Cheers. All right. Thanks everyone for coming out. So my name is Michael, as Patrick introduced me. I just want to say thanks to Hackfest and thanks for Patrick for having me out here and having me speak on HTTP2 DDoS. So I'm going to be talking about clogging the future's series of tubes. So I'm focusing on HTTP2, and it's a new protocol, so what sort of new attack vectors does it bring? What sort of considerations need to be made when deploying this protocol? And so the inspiration for my title actually came from, why isn't this updating? Yeah, let's see if it works. Okay, oh, yeah, okay, we're in better shape now. All right, so the inspiration for my title came from a man named Ted Stevens, who is an Alaskan senator, and he's famously quoted as saying that the internet is basically a series of tubes. And it was a terrible analogy because it showed how little he knew about the internet, despite being someone responsible for regulating it, especially in terms of net neutrality. So you can look him up. He's got some interesting quotes. I just always laugh. So a little bit about me. My name is Michael Bennet. I am a DDoS strike consultant at Security Compass. So my job is to actually launch DDoS attacks. So I work with clients and I try to assess what their DDoS mitigation is like. So whether it's actually configured correctly, you can think of it like a pen test for a DDoS mitigation system. So one of the ways we actually test them is launching real DDoS attacks. And they're not small scale. I've launched attacks as large as like 28 gigabits per second for a UDP flood. I was testing another client the other day, and I had 5 million active TCP connections to them. So the real DDoS attack, so it's kind of cool. So I've been living and breathing DDoS for the last couple of years. And before I go on, I just want to say my talk is sponsored by Sauron Monitoring. If you're not a Lord of the Rings fan or don't know anything about it, there's going to be a lot of references you're not going to get. But, you know, Sauron Monitoring, nothing misses or nothing escapes the all-seeing eye. So for the agenda today, I'm going to introduce HTTP2. I don't know how many people necessarily know about it or know what the new features are. So I'll briefly intro that. And then I'm going to focus on two of the bigger features of HTTP2 and kind of, you know, what can I abuse with that to launch any sort of new style DDoS attacks. So what does DDoS look like today? I'm sure a lot of you have heard about the Dyn attack, some of the terabit scale attacks. So today, historically, DDoS attacks have been separated into volumetric and application layer attacks. So volumetric, really high bandwidth, and application layer, kind of low and slow with a high number of request rates, but generally low amounts of traffic that are designed to starve a web application of its resources. But there's actually a scary trend of those two converging. In the industry, we're actually seeing application layer attacks that are hitting the gigabit scale, sending hundreds of thousands of requests per second to a single server, and even like DDoS mitigation appliance, and it's just toppling them over. Even in addition to that, I'm sure a lot of you have heard about the Mirai botnet and IoT botnets. So that's another major scary thing that's kind of happening where you have a new breed of bots, and IoT manufacturers are basically just producing bots for the internet because they're creating them insecurely, default passwords, and they just get scooped up. So I liken them to the Isenguards, which in Lord of the Rings was a place where orcs were manufactured, the Uruk-hai, and then, yeah. If I get too much into Lord of the Rings, someone shout at me. So we've seen, because of these giant botnets, IoT manufacturers are manufacturing millions of devices that are just insecure with default passwords, and those are getting scooped up into these botnets. And so we're seeing some crazy scale, massive DDoS attacks. So there was a record-breaking one against Brian Krebs' website that reached 620 gigabits per second. The interesting thing was that it was not spoof traffic, which is more typical for a volumetric DDoS attack. It was a combination of full TCP connections, some GRE protocol flooding, HTTP requests, so a real mix of everything. So it was probably the like several vectors of attack, and it was to the point where Akamai, their paying customers were being affected for them trying to mitigate it, so they had to kick them off, which is unfortunate, but they were giving him service pro bono. And even shortly after that, a hosting company called OVH reported that they saw a terabit DDoS attack. So this is actually a really scary one because a lot of these mitigation providers boast about having something like a 2 terabit capacity backbone for mitigating attacks. And now we're seeing attacks actually get into that scale. So it's kind of like who's got the bigger gun at this point, and the botnets are catching up. And then I'm sure, like I mentioned earlier, the massive Dyn attack that showed how the internet has a single point of failure. Now, while it wasn't really most of the internet, like people will sort of cry about, in a sense, but it was a lot of major websites, some of the top websites that went down because Dyn went down, because they couldn't handle a massive DDoS attack against them. And this is a company that also offers DDoS mitigation services. So with all of these new types of attacks, we're seeing new protocols being used. GRE flooding is becoming more popular. The STOMP protocol, which is a UDP-based protocol, is also being used. One of the newer protocols is HTTP2. So first off, what's new in HTTP2? So its focus was on performance and loading web pages a lot faster and improving the performance of just browsing the internet. It also aimed to undo some of the hacks that a lot of developers were doing in order to speed up page load times. And that's things like inlining static assets into a single file so that when the first request comes in, the response basically has everything that a browser needed to render the page. So for HTTP2, it's now a binary protocol, as opposed to the text protocol that HTTP 1.1 was. One of the bigger features is multiplexing. So you can now use a single TCP connection to make multiple simultaneous requests that are served as streams, versus the classic behavior of browsers of opening multiple connections, up to 6 connections, and doing a bunch of requests and then reusing those connections or creating new ones. So there's a lot less overhead. It also introduced the notion of flow control, very similar to TCP's congestion control. So because you're making so many requests over a single TCP connection, it gives both sides a mechanism for restricting how much data gets sent back in response to those requests. It also has compression built in through a system, or I don't know if it's a protocol, but it's called HPAC. And so the idea is that everything in the HTTP2 stack can now be compressed, including headers, which was a big step up from HTTP, where only the body could be compressed. Another major feature, the major ones are the ones I'm going to talk about, so that's why I'm pointing them out, is server push. So the idea that the server can actually push you requests or push you responses without you ever asking for it. And this is to undo the hacks where people were just loading or overflowing a page with inline static assets just to get it all out at once. So now you can actually configure your server to push the static assets that your index page would need in order for it to render properly and actually speed up the time before the client even requests those pages. And finally, another major feature is priority. So there's a notion that you can create dependencies between different files so that you can enforce some sort of order at which resources are loaded. So you can kind of think of HTTP2 as the love child of TCP and HTTP 1.1. I mean, it still encompasses a lot of everything that HTTP 1.1 does, but now it's binary. It's got congestion control or flow control. You even have to ACK some of the data that you receive in order to start receiving more. So it's a very, very close mix of the two. So HTTP2 is very new, but people are starting to look at the security of it. And even in the RFC, which I believe was only finalized last year, there's a section dedicated to security concerns and how to run an HTTP2 server so that you're not overwhelming it or not overwhelming your clients connecting to it, and how to protect yourself. And there's even some considerations for breach-style attacks where padding is actually built into the protocol itself. So some thoughts around security have gone into it. Unfortunately, a lot of the thoughts and suggestions in the RFC are only suggestions, so it's not guaranteed that everyone's going to follow it to a T. So there's a company called Imperva that actually did some research, or did some initial security research around HTTP2. And so they had some interesting findings. Some of the more interesting ones are basically it enables a new style of slow loris type of attacks because TCP connections are long-lived and there's the idea of a new flow control window that can be abused for a new kind of slow loris type of attack. They also found that some dependency loops could be created where you rapidly shift dependencies and priorities in some of the resources you're requesting to cause a loop, and that would just kill the server, basically, eat up all the server's resources. And with any compression algorithm, there's a compression bomb. So you could abuse HPAC to actually send a highly compressed file that decompressed to gigabits of data and blew up a server, basically. So I'm going to look at server push. And so I think of this as getting more than what you asked for, because you're making a single request expecting one page and you're getting a bunch of resources. So it allows you, like I mentioned earlier, it allows you to send the resources that you expect the user to need. So that typically includes a lot of assets, static assets, but it can also do more interesting things like pages you expect the user to visit. So if you have a limited set of pages that the current page connects to, you can actually preload those pages as well so that the experience for the user is really quick. Clients do get control over how much data is sent to them, and that's through the flow control mechanism. And Google's actually released a document of some very good sort of best practices when it comes to actually running an HTTP2 server. But I'm not going to get into that. I'm actually going to show you what HTTP server push looks like. I'm getting really hot up here. All right. So I haven't prayed to the demo gods yet today, but hopefully this goes pretty well. I was up pretty late last night, as some of my friends will attest to, but I think I finally got it all working. So what I've written here is just a Python client that has an HTTP2 implementation. It's built around another library that implements the protocol, and I wrapped that around an asynchronous library called Tornado. So all this is going to do is show you the difference between HTTP 1.1 requests, 2 with no server push, and 2 with server push. How visible is that? Can you guys read that? That's okay. So not too flashy. I mean, let's make it a little flash here. Oh, of course I forgot to do this. So you can see my requests come in. And so what we see here is that HTTP 1.1, I'm just requesting the root page. It's about 47 kilobytes that I get. HTTP 2 with no server push, it's about 46, 47. So we got a little advantage from compression there. But with server push, I'm actually getting 1.2 megabytes back from the same request. They're all making the same request. So that's a huge jump in the amount of traffic that's just getting sent back. So actually, right now I have an Apache HTTPD server configured with server push. So I actually have it configured for an ideal situation, or what Google depicts as an ideal scenario, where it only loads mostly the JavaScript assets. So I actually have the naive kind of configuration where absolutely all the static assets are being loaded. So with this, you can actually see that my total traffic jumps close to 7 megabytes for a single request. And this is likely to be, this is going to be a common configuration you see in the wild, where people think, load all my static assets at once, and the user gets everything. So now we're making bytes of a request return back 7 megabytes of data. Oh, come on. There's a video too, and now it's all ruined. All right. It's going to be the bane of my existence. Oh, wait, there we go. All right. There we go. Server push. So for our ideal configuration where we're not setting absolute all the static assets, we get about 26 times the amount of data that you would for a normal HTTP request or with no server push. In the worst case scenario, it actually works out to be 149 times that data. And this isn't too huge of a site either. This is just our Security Compass site. I can bring it up. Had a browser ready. Yeah, that's the one. So this is the site I'm loading. So it's our company website. It's not too crazy. It's got I think it's got, well, you can see actually I received 91 pushes. So it pushed 91 different assets to me. And if you ever want to play around with HTTP2, Google has pretty good support for it, Google Chrome. So you can see all the assets are being pushed here. So we're getting 149 times the regular amount of data. That's a huge amount. The issue with server push is that caching, client-side caching, is now more complex. You're pushing all of this data without knowing what the client already has cached. And there's nothing in the protocol, nothing in the spec that details how to actually do that properly or cleverly or in some sort of an intelligent way. So caching schemes are now a little more complex because you don't necessarily want to send absolutely everything because you get 7 megabytes of data you didn't ask for, especially when you've just requested that page because you already have it all cached. Additionally, the server push logic typically needs to be implemented at the application layer. The application layer needs to decide what gets pushed, and it uses, the common implementation is that it uses link headers to tell Apache or whatever else you have running in front of it to actually push those files. And if we're going to move forward with defending against server push, it actually needs to be tied to your DDoS mitigation. So your DDoS mitigation needs to be aware of what actually is supposed to be pushed and be able to detect when a single user might be purposely being pushed too much data. And so the imbalance between the request and response is actually pretty similar to something seen before. So amplification style DDoS attacks, where you send a very small request and you get a very large response. For HTTP2, it actually, oh, damn it. Man. All right, I'm going to keep going and hope that this loads. So the amplification factor for server push was actually about 68 to 1. There we go. A typical DNS style amplification attack was actually at a ratio of about 70 to 1. So we're right on par with DNS amplification attacks seen in the wild. But this is TCP, so we can't use any sort of reflection or anything like that. So really, what's the value in actually trying to do this amplification attack if you're only going to DDoS yourself? So the way I see it is you can still flood the egress pipe out of the server or out of the company's infrastructure. If they have a lot of load balance servers that can process a lot of requests, you could potentially flood their outgoing pipe with so much data that actual legitimate traffic can't get out either. And in a different scenario, I actually see this being used to attack some of the large cloud providers. If I spin up 100 servers in AWS or something and start requesting out to all the CDNs that support HTTP2 push or server push, which right now I believe is only Cloudflare, then I can actually get that to send back a ton of data. So in my testing, I had a single server from running on Google Cloud send back 50 megabits of data per second at a constant rate, just using HTTP2. So 100 of those, and I've now hit 5 gigabits per second, and I can keep going up from there. And it wasn't a big machine either. So I could potentially amplify that more, tweak it some more. And so we're already seeing potential to launch some huge attacks, even against cloud hosting providers with HTTP2. So moving on, one of the other features, I gotta keep track of time here. One of the other major features is multiplexing. And so it's one connection to rule them all. You're no longer using 6 simultaneous connections to try and load resources faster. Multiplexing allows you to have concurrent requests and requests like multiple resources simultaneously. And it'll handle the logic of interleaving them, similar to how TCP would at the layer 4 level. In practice, technically the streams, I think, go up to 65,000. The protocol allows it, but in practice, they're limited to about 100 streams per connection. And that's just so that the server doesn't allocate or over-allocate resources to a single connection to try and handle and serve all of these streams. So with multiplexing, we get some reduced overhead from both sides. And also, inherently, the connections are long-lived. This protocol specifies that you should keep your TCP connection open for the life of a session. So basically, for as long as the user has that website open in the browser. So for long-lived, this kind of opens us up to another style of slow loris attack. The intended nature is that these connections stay alive for a while. And you can actually see, I don't know if I should switch or if I'm going to have issues. We'll see. So in Chrome, you can actually see my connection to the host, and basically stays alive for a while. I just died there. I might not have my server configured right. But even if you go to somewhere like, how come I? You'll see that this connection basically stays open for as long as I have this tab open on Akamai's site. And that's so that, you know, if I browse to a new page or anything like that, it doesn't have to wait that initial TCP three-way handshake before I can start sending the new resources required. Even if I close it off now, you see it lingers a bit, and then it should go away. It stays open even longer. So this is an issue because now these connections are supposed to be open. With classic style slow loris attacks, the connections are held open for longer than normal periods. And this usually results in an HTTP 408, which is request time took too long. So we had mechanisms in place for HTTP 1.1 to detect this kind of malicious behavior. But now with HTTP 2, because these connections are meant to stay open and stay idle, it's a little more difficult to tell what's legitimate traffic and what's not. So additionally, with less overhead, this also becomes a benefit for the attacker. Without any sort of tweaking, without any sort of tweaking to the kernel stack, you can actually, a large HTTP flood with HTTP 1.1 can easily eat up a lot of the TCP connections available on your system, or the open file handles. So normally, if you're attacking, you'd need to tweak how many open file handles you can have so you don't run out while you're sending requests. With multiplexing, I only need a single connection, and I can send out 100 simultaneous requests. I can open multiple connections and amplify that even more. Now it's black everywhere. All right, let's go with this because this is at least visible. It's not a good day for me. And now I'm at the beginning. All right. So less overhead. Sorry, I'm losing my place a lot because of this. I'm just going to keep it at this. Imagine it's full screen. Yeah. I mean, I can hide this. Maybe zoom a bit. No. Yeah, okay. All right, so less overhead. You don't need as many TCP connections. Makes it easier to actually launch more requests at a higher rate because you also don't have to wait for that full TCP handshake each time you're sending a request. I need to find my place in here. There. I'm going to leave it at that. This seems to be working. So, now that you're only using a single connection for your attack, you cannot simply just limit concurrent connections, which was a pretty typical mitigation method for slow LoRa style attacks. I gotta manually play the video. These attacks are also harder to detect because, again, single TCP connection, you're not seeing abusive behavior of hundreds or millions of connections being opened, which is obviously malicious, or even thousands of connections. Before you could safely limit concurrent connections to maybe 6 to 10 for a single IP or a single client, as browsers would only use up to 6 concurrent connections. So you have a reasonable guess at what legitimate behavior looks like. But now legitimate behavior is kind of masked by this single connection. So one common method was using IP tables. It has a con limit module. And that's actually a pretty good defense because it blocks it before the application layer could even has to handle it or detect it. So it offloads some of that to the more performant firewall. And you can even offload it to an external firewall. But we kind of lose that mitigation now with HTTP2. So what defenses still work? Actually, before I move into this, let's demo. Why are you over here? So I wanted to show actually how much traffic you can generate with HTTP2. Oh, perfect. Yeah, I need some of that. Ready? Yeah, what is it, 9:30? Perfect. I mean, these slides aren't working, so I wanted to demo how much traffic actually gets generated. Cheers. Cheers. My colleague too, so he needs it. Thank you. So I want to show you how much traffic you can actually generate from a single attacking agent. So we're back in my environment. So I'm running this script, which just rotates through all of the assets in a file and requests it over a single HTTP2 connection. So hopefully this works. And of course it doesn't. There we go. All right. So on the left here, you can see this is a tool called nload. And it just displays incoming and outgoing traffic for your adapter. So you can see here that I'm pulling a solid 28 to 30 megabits per second, just rotating through all these requests from a single agent. And this server is just, it's like a 2 CPU, 7 gigs of memory, hosted on Google Cloud. You can see at the top there, my CPU percent usage is only at 5%, so I could even push the server a little more. But I'm even peaking at 50 megabits per second. So you can see I'm pulling a lot of traffic from this server with just a single client. So you can see some stats. I'm only sending about 100 requests per second. 65 of them are getting finished. I think I can actually tweak that to be a little better. But either way, you see, like it's pretty easy to get 50 megabits of data from this HTTP Apache server too. And oddly enough, Apache runs HTTP2 a little faster than Nginx. So, what defenses still work? I wanted to look at both Nginx and Apache 2 to see what some of their rate limiting modules still actually are valid for HTTP2. There's a lot of security modules. One being mod security for Apache. There's mod evasive as well, and then Nginx has some built-in ones for limiting concurrent connections and also request rates. So I wanted to make sure that those are still reliable. So I started with Nginx. And so there's really two modules for Nginx that can kind of help. There's the limit connection module, or limit con, and that limits it originally was developed to limit how many simultaneous connections you could have to the Nginx server. Nginx actually adapted it for HTTP2 to count single requests as a connection. So it was actually smart with adapting it. So this module still works, and we can actually see that. There we go. So you actually see it in action. So I'm only getting about 20 megabits per second, a little less than last time. Then if I kill this, you'll see that I'm actually getting a lot of 503s. And that's that connection module kicking in, limiting the number of requests I'm sending per second. Similarly, there's the limit request module, which originally was designed for limiting requests. They kind of now have the same function in HTTP2. It'll limit the requests based on a rate, allows some bursting. So it's still an effective measure. And I'll demo it, but it looks the same basically. So Nginx is still actually pretty safe for blocking some of this overuse of the server. The only issue is that now a lot of the defense is happening at Nginx, at the application layer. So it's still possible to flood it with requests so that you exhaust all the Nginx workers. So it's not ideal that we're blocking it at the Nginx level. Ideally, we're pushing it out a little further to the edge of the infrastructure. So any appliances, DDoS mitigation appliances that you'd have in place, or if you're using a third-party provider, limiting the number of requests is essential for blocking and limiting the impact of HTTP2 DDoS attacks. So I also looked at Apache's server, HTTPD. So there's two modules I looked at, the mod evasive and mod security. And I don't know if I'll demo it, but they work. I'll tell you they work. And that's because Apache's model or the way these modules work is they actually operate only on requests anyways. So they don't even care about connections. There's, I believe, a 5-phase process for processing a request in Apache, and it hooks into those phases to count requests. So there's no changes needed for them. Mod evasive actually hasn't been updated for a number of years, but it's still a viable means for defending against HTTP2. So, is all hope lost? At this point, I don't think so. I mean, I see some advantages for me as an attacker. I can definitely use some of these CDNs that are allowing for server push. And even the 40 to 50 megabits per second wasn't even using server push. It was using a single connection and just making all of those requests. So I see an advantage for me in a sense. We'll definitely need to adapt some of the defenses that we'd have in place to detect some of these more malicious behaviors. Like there's no reason for a single IP to be pulling down 50 megabits of data at any time, unless it's a really huge data file or something like that. So we'll have to focus more on the behavior of the connection and the client and what they should be doing at the time in order to actually determine whether they're a bad actor or not. Additionally, like any sort of third-party rate limiting, so if you have an appliance that's in charge of it, or a third-party provider like Akamai, that is going to be a key in defending your infrastructure against these kinds of attacks. And I lost my place. So yeah, one of the major things is also, because we lost detection for high number of concurrent connections, and even for pulling a high number of requests, there's going to be bursts for a normal user, especially with server push, especially with loading a really complex page with a lot of different assets. So it's harder to detect what a good user looks like. So monitoring the outgoing bandwidth for a single IP over a period of time is going to be a good identifier of a potentially malicious user. So that's actually all I have for today. I wanted to post a link in here. So all of this sort of HTTP2 lab is up on my GitHub. I think it's, let's see if I can find it. There it is. Yeah, so if you're interested in exploring some of the stuff, playing with some of the tools, don't use it on anyone. You're not allowed to. And if you do, don't say you got it from me. So you can play around with it. It's mostly Docker-based. I will tell you that setting up HTTP2 servers was a huge pain because OpenSSL is outdated everywhere. And you need OpenSSL 1.0.2 minimum, because HTTP2 requires the ALPN protocol or feature in order to actually work. So recompiling everything and compiling servers was probably the longest part of exploring some of this. It's what kept me up last night trying to get these demos working. But luckily, I fleshed it all out, figured out all the issues, and I have some nice Docker files which will build latest versions of Apache and with HTTP2 support out of the box. And also, there are the Python clients. So I do need to update this a bit, add some documentation so it's a little easier to use. But there's some nice HTTP2 clients in there for you to play around with. And if you want to keep exploring, I'm going to keep exploring some of the features of HTTP2 because there's a lot to explore. I welcome everybody else to and build off of what I have here. If you do find something, it'd be cool if you let me know because I could use that too. But yeah, this is open source. Anyone can grab it, so feel free to. And that concludes. Yeah, you can find me on Twitter. I'm at Bennetar. Are there any questions? I'll field some questions. I have some time. No questions? Anybody have questions? Cool. All right. I'm going to go sleep. Thanks, everyone.